Okay, good evening, students. We are going to discuss today 2019 and 2021 A-level structured essay questions. We can basically revise the first unit and the second unit along with this structured essay discussion. And this is our 2019 structured essay. So the first part is they are giving short questions. Now the question is asking, the following questions are related to the elements of the second row of the periodic table. So you have to answer these questions using the second row elements, right? And write the symbol of the element in the space provided. So that is bolded. Because let's say answer is lithium for some question, right? You can't write lithium in words, in letters, right? You have to write L, capital L, simple I. You can find these essay questions in your tute also. If you check the page number 49, you can find this structured essay, right? So I'm going to go to the tute and do the question. Let's start the question by writing second row elements in the periodic table. So what are these elements? If you go to the first row, you have hydrogen and helium. So second row means starting from lithium, right? So lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. These are the second row elements. Anyway, you will be given a periodic table. So this is your second row. First thing they are asking, right? Identify the element that has the highest electronegativity. So you have to disregard the noble gas. So in A-level syllabus, you are not learning any value for the noble gas electronegativity, but you can calculate a value if you need. But anyway, for A-levels, you don't need that, right? So if you ignore the noble gas, which is neon, so you have to consider other 7 elements. So what is the one with the highest electronegativity? We all know that one even from O-levels. It is fluorine. Understand? So fluorine is the highest electronegative element. So this is the answer for the first one, right? Fluorine. So electronegativity, what will happen to the along the period? Electronegativity increases from left to right. So if you want to write a small sentence there, right? Managing the space in the tute itself, you can write electronegativity increases across the period. Okay, electronegativity increases. So electronegativity basically means ability to attract electrons. So as the size of the element decreases, size of the atom decreases, right? And the nuclear charge increases, right? That ability to attract electrons will increase. That's what happened with the fluorine. If you check the size, fluorine is the one with the smallest size in the period. If you ignore the neon, right? And it is the one with the highest nuclear charge, right? And then it should have the highest ability to attract electrons in a bond. In other words, electronegativity. Understood that one? So fluorine is the highest electronegative element, right? Then you go to the next one. It's asking you to identify the element that has an allotrope which conduct electricity. The electricity conducting allotrope, right? So if you go to the allotropic forms, now you already know from O-levels also, carbon is having 2 allotropes, diamond and graphite. So in A-level syllabus, you will learn another allotrope called fullerene. Okay, anyway, you are learning these things later. But we all know that electricity conducting nonmetal is graphite. Understand? So they are asking about that element. So if you write graphite in the space, you will have no marks. Understand? So they are giving you instructions. They are asking you to write the symbol of the element. So element is carbon, right? So you have to write the symbol capital C. Is that clear? So that will be the answer for the second. This is the one you have to write for the second, carbon. Okay, then you can write there, what is that compound, right? What is that compound? What is that element is graphite. Graphite is the element that conduct electricity. Okay. So allotropic forms means different physical existence of the same element. What the example we know for now is diamond graphite example. So there are several other examples you will learn in unit 6. Okay. Right. Then go to the next one. Identify the element that forms the monoatomic ion largest in size. monoatomic ion, largest in size, and they are giving you an instruction. This must be a stable ion, right? So if you consider the ions of these 7 elements, right? So lithium is forming lithium plus. Okay, so you can see lithium plus, and beryllium is forming beryllium 2 plus. Boron is not likely to form an cation, right? So let's leave it there. And carbon, we know carbon doesn't make cations or anions. No, you can't write C plus, C4 plus. That's wrong. Understand? So, but nitrogen forms N3 minus, oxygen form O2 minus, fluorine forms F minus. So these are the stable ions we know in that, right? Obviously, we can ignore this lithium plus and beryllium 2 plus because these are cations. These are small. Okay, cations are smaller than their parent atom. They will be very small actually, right? And then anions are larger than their parent atoms. If you consider these 3 anions, the size is changing in this, right? N3 minus is the largest one. So you can't write N3 minus in the space, okay? Right? So what you have to write is the symbol of the element. So you have to write capital N in the space provided for the third question. So N3 minus is the largest stable anion. Stable ion. So they are not asking for anion, but actually anions are the one they are with the larger size. So you can just revise our previous questions on this anion cation. The fourth one is telling identify the element that has no p electrons but has a stable s configuration. No p electrons but with a stable s configuration. So if you check the elements, can quickly understand their electronic configurations. This is having 2s1 and this is group 2, so 2s2, and this one is 2s2 2p1, like that. Then the p electrons are filled, and the nitrogen is 2s2 2p3, and neon right here 2s2 2p6. So if you look for the stable configurations, you can find stable configurations in these elements: beryllium, nitrogen, and neon. So you know that their sub-energy levels either fully completed or partially completed, half completed. Then if you have half completed or full completed sub-energy levels, then they will be stable. That is the logic. Okay, you know that neon has a fully packed energy level. But nitrogen, you will see 2p3 is filled 1 electron per each orbital. This is also stable. Understand? So they are asking for us for an element with no p electrons. So then you have to remove this neon and nitrogen because they have p electrons now. So what's the other element left? It is beryllium. Beryllium is a stable configuration, 2s2, right? But it is not having any p electrons. So this beryllium is the symbol. You have to Be is the symbol. You have to write in the as the fourth answer. Okay, and then look at the fifth one. Identify the element that has the highest first ionization energy. First ionization energy. So ionization energy increases across the period, but it increases in a zigzag pattern. Zigzag pattern. So if you start from lithium, this will be beryllium. Beryllium has a stable configuration, and boron configuration, the boron ionization energy, first ionization energy is a little bit lower than beryllium. Right? Beryllium had a higher value because of that stable configuration we wrote. And then you have carbon, which is higher than beryllium. And then nitrogen, oxygen again have a little bit lower value. And then fluorine. And finally, you have neon, which is having the most stable configuration here. So when you consider the all 8 elements of the second period, right? So what is the element with the highest first ionization energy? Is going to be neon. So neon is the symbol you have to write for the fifth answer. Okay, Lama? Neon. So ionization energy, remember, it increases across the period and it is increasing in a zigzag way. Okay, so last week I remember we discussed in our paper class that now we expect a gradual increment, but because of the stable configurations, the beryllium Even with a lower nuclear attraction, it is having a higher first ionization energy. If you consider the nuclear attraction, boron having a higher value, but beryllium has a high uh, first ionization energy because of its stable electronic configuration. So that's where we understand that ionization energy depends on both electronic configuration and the nuclear attraction. There are two factors affecting on that. So if you consider, let's say, radius or electronegativity, it is only depend on the electron attraction, nuclear attraction. Understand? But this property, first ionization energy and as well as the electron gain energy also, they both depends on nuclear attraction, then as well as on the electronic configuration. So both are affected. Right? I hope you clearly understand that one. So that's the answer for the fifth one. Go to the last one. It's asking you to identify the element that forms mostly electron deficit trigonal planar covalent compound. Now they are kind of giving you a big thing now, right? Element that form mostly electron deficit. Electron deficit compounds you can find for these two elements, beryllium and boron. Beryllium forms BeCl2. Boron forms BF3. I hope you remember these two molecules because we especially look into these two molecules in our BSc PR theory discussion. Remember? Because why? Beryllium has only two covalent bonds. It's very simple. Electron deficit. Usually, atoms are like to have, there are 8 electrons in the valence shell, but beryllium, interestingly, having only 4 electrons. Boron also the same. Remember? Electron deficit, right? Only 6 electrons are there. So now they are adding trigonal planar covalent, right? So trigonal planar, you can see now BF3 is trigonal planar, no? So then boron is our answer for the last question, sixth one. You have to write the symbol capital B. So like that, you have to write only the symbols. Don't write any compound or any name or anything else. You only have to write the symbol. So follow the instructions and you can see it's very easy. SO3F2. So skeleton structure is given. Right. So we can use our practice to draw this question, draw this Lewis structure. Okay. So fluorine, normally it is always actually it is the it becomes as a peripheral atom. So when fluorine is there as a peripheral atom, right, it keeps 3 lone pairs on that. Okay, it keeps 3 lone pairs on that, and it is always forming a single bond. That is a fact. Okay, we know. And then if you consider this sulfur and oxygen, these things, when oxygen is there as a peripheral atom, if there are no charges shown here, right, usually it is making a double. So when oxygen makes a double bond, it keeps 2 lone pairs. Okay, when oxygen makes a single bond, it will be having a negative charge. There is an instance that oxygen could make a triple bond also. In that case, it will have a positive charge. Understand? So this one is rarely happening in the Lewis structure question because it is making this structure unstable. More electronegative oxygen having a positive charge. Okay, so here we can take a guess and go with this second option, right? Of where oxygen makes double bonds, right? So let's say oxygen makes double bonds here. Then you have to put 2 lone pairs for each oxygen. Right now you can check on sulfur, right? So if you check about the sulfur, sulfur should keep 6 electrons in the valence shell. You can see here 1, 2, 3, 4, 5, 6. 6 electrons are there. So sulfur will have no charge. Understand? So then you can work on this oxygen. It should also have 2 lone pairs, just like water. In water molecule also you have a similar structure. So when it make 2 bonds to the either sides, it is keeping 4 electrons as 2 lone pairs on the oxygen. Is that clear? So this is the Lewis structure. With practice, you can take this on within seconds, right? But I'm going to show you Lewis structure, how to use the Lewis method for this one. Okay. So in the Lewis method, what first you have to do is finding the valence electron. Sulfur is giving you 6 valence electrons. there are 3 oxygen atoms which is giving you 3 into 6, 18 valence electrons, and 2 fluorine atoms are giving you 7 into 2, or you can say 2 into 7, 14 valence electrons. So if you add them all, you will have 38 valence electrons. From that, I will draw the skeleton again. From that, you have to subtract electrons for these bonds we already have shown. So you have 1, 2, 3, 4, 5 bonds. That means 10 electrons. If you subtract, you will have 28 electrons. That means 14 electron pairs. So those electron pairs you can apply to the peripheral atom until their octet become completed. Right? So I applied here 12 electron pairs. So the remaining 2 pairs I'm going to apply to this oxygen. Okay. So then we are looking at the central atoms to see whether their octet is completed. So if you check for the oxygen, it is completed. Octet is okay. Sulfur also octet is fine. Right? So then what you are going to do is you are going to check the formal charges. So you check the formal charge here. 1, 2, 3, 4, 5, 6, and 7 electrons are there now with oxygen. So it brought only 6, but now there are 7 with that now. 8 electrons are there in the valence shell, but on oxygen you have 7 electrons. So that means 1 extra electron. So you have to put a negative charge on that. So in that way, this will also be negative. Now if you apply the same logic on central sulfur, 1, 2, 3, 4, only 4 electrons are there with sulfur. Even though there are 8 electrons, only 4 are coming from sulfur. But sulfur brought 6 electrons when it is coming to make this structure. No? So that means 2 electrons are missing. Right? So those 2 missing electrons, we are writing here as +2. Understand? So 2 electrons are missing. So now what we do, sulfur is an element that can violate or that can make more than 4 bonds, or they can violate octet rule by keeping more electrons. So sulfur, what is going to do? It will make 2 more bonds with oxygen until the charges are neutralized. So then you will get this same structure we got with our practice. Is that clear? So choose any method you prefer and do, right? With the practice, you will realize this is the easiest and fastest way. Okay, so this is the Lewis structure they have given. So you have to draw 2 more structures for this one. So I explained and taught you a method to draw these Lewis resonance structures quickly, right? The method is simply this. You count how many 5 bonds are available, right? And you can see here you have only 1 5 bond. So what you have to do next is draw several skeleton structures and change the location of the 5 bond. Okay, change the location of the 5 bond. So and put the 5 bond where applicable. Understand? So that is how you take the number of structures, right? And then you can do the same thing with the lone pairs, because lone pairs are also going to be constant. Right? So here you can see you have 5 lone pairs. So in every structure you will have 5 lone pairs. So this method is applicable, 100% applicable when you have central atoms as nitrogen, oxygen, or carbon, some element that must follow octet rule. Right? But if you have a central atom, let's say sulfur, phosphorus, or something, then you may draw more than the given number. Now that means sulfur can make more than sulfur can violate octet. No? So then it will make obviously more than the number of 5 bonds it is given in the given structure. Understand? So here the number of 5 bonds is fixed because nitrogen, oxygen, those elements can't violate the octet rule. Okay, so that is the foundation of my method, right? So let's draw some skeleton structures and, like I said, apply the 5 bonds in possible suitable places. So you are not going to apply 5 bond here, okay, because hydrogen is never going to make 5 bonds, no, it only make 1 bond. So you can apply 5 bond here. This is a possible location. And there is another location. You can put it between oxygen and nitrogen, no? You can put it over here also. So these are the 2 possible places you can apply the 5 bonds. I hope it is clear. Now, like I said, you can put the lone pairs also in suitable places. Here, you can put a lone pair. You can put 2 lone pairs and another 2 lone pairs here. Now, you can go with the charge. Here, you will have a +1 charge, and here you will have a minus charge. You can put another lone pair for this one to complete the octet, and 2 lone pairs here with a minus charge, and lone pair here, and lone pair here with a positive charge. And when you draw the Lewis structures, remember to put this double-headed arrow to say that these are the resonance structures. Right? So you will be given marks for these two, and they have asked an additional thing. They are asking you to mention the unstable one, especially. Okay, unstable one. So what is the more unstable one? It's going to be the second one, right? You have to write unstable near this. So why it is unstable? You can write a reason for that. What is the reason? You can see here, oxygen is having a positive charge. More electronegative oxygen has a positive charge. That is the reason. That is the reason. Understand? Because in both structures, this nitrogen is having a negative charge. But the only difference with the structures we draw, oxygen has a positive charge in this second structure. Okay, octet rule must be followed by CN. This is the structure, and it's asking the usual things: a number of VSC-PR pairs, electron pair geometry, and electron pair geometry shape. Then finally, they're asking for the hybridization state, right? Okay, so if you take the first structure, oxygen here is having 2 lone pairs and 2 bond pairs, right? So here 1, 2, and another 2 here. So this one is having 4 VSC-PR pairs. 4 VSC-PR pairs. Okay, if you have 4 VSC-PR pairs, its electron pair geometry is going to be tetrahedral. Tetrahedral. Okay, and the shape is going to be angular or bent. You can say bent also. So don't misunderstand this one. It's not linear, even though it looked like that. You have to remind water molecule. Water also have 2 lone pairs, but we draw those 2 lone pairs in the same side to make sure that you understand it as angular. But when we give structures like this in the questions, they are applying the lone pairs in the either sides. That doesn't mean it is linear. Okay, take it properly. And as we know, if it is tetrahedral, hybridization is going to be sp3. sp3. So all p orbitals and the s orbital of the 2s orbital of the oxygen has undergone this sp3 hybridization. Understand? And after hybridizing, 2 hybrid orbitals are going to make sigma bonds, and other 2 hybrid orbitals are keeping the 2 lone pairs. That's what happens. Other 2 orbitals are keeping the lone pairs. Right. Then you can do the same thing about N2. N2 is having 3 VSC-PR pairs. You can see a lone pair and 2 bonds. We consider double bond as a single unit. Double bond as a single unit, okay? And then this one is trigonal plane. Shape is angular or bent. And hybridization is sp2. So even though they have the same shape, angular shape, their angles are going to be different, no? Remember? So this one is having 109.5 minus 5 degrees. That means 104.5 approximately. Okay, so this one is having 117.5 approximately. Angles are different. And then you can go to the next one, C3. This one is having 2 VSC-PR pairs, and it is going to be linear electron pair geometry and linear shape. Hybridization is going to be sp. Okay, hybridization is going to be sp. And finally, you have this N4. You have 3 VSC-PR units, trigonal planar, and shape is also going to be trigonal planar. Hybridization is sp2. sp2. Understand? So let's talk a little bit about this sp hybridization. Carbon is having this 2s and 2p orbitals, right? So if you take the carbon electronic configuration, it is 1s2, 2s2 and 2p2, right? So 2s2 and 2p2 are the valence shell electrons. This is the ground state of carbon atom. And carbon will become a state called excited state, right? And push one of these electrons to here. Then it become like this, okay? And then they undergo a thing called hybridization to give hybrid orbitals. So if all 4 orbitals are hybridized, we call it as sp3 hybridization. 1s and all 3p orbitals are undergoing hybridization. But here, this carbon can't undergo sp3 hybridization. It has undergone sp2. The reason is only these 2 orbitals are hybridized. Only these 2 are hybridized. So other 2 p orbitals, they remain. They keep to make 5 bonds. They keep to make these 2 orbitals to make 5 bonds. And these 2 are hybridizing to give you 2 equal orbitals. 2 equal orbitals, sp orbitals. Those sp orbitals are arranging linearly in the space with 180-degree angle. And there will be the other p orbitals perpendicular to this one. One is along the board and other one is perpendicular to this, to your side. Okay, so that's what we call as sp hybridization. Sp hybridization. Is that clear now? Because this knowledge will be important when we are doing the next parts. Okay, so any question up to now? Nothing, right? So we are going to go to the next page, and it is asking about the orbitals that participated for the bonding, the sigma bonds. So first one they are asking here is the bond between fluorine and oxygen, F and O. Yes, one of you asking why did I subtracted 5 degrees? Because there are 2 lone pairs now. For 1 lone pair, we subtract 2.5. Okay, Pute? For 1 lone pair, we subtract 2.5. Right, so let's come back to the question. And F and O1, this bond is formed between, we can say, now fluorine is having 3 lone pairs also. So you can, one option you can say 2p and sp3. Or you can say sp3 and sp3. Because you can consider peripheral atoms are also hybridized if necessary. And if you don't like that one, you can say peripheral atom is not hybridized also and go with the first option. If you consider peripheral atom as hybridized, then you can write sp3. So what I recommend is usually, because you're less likely to get this one wrong, but anyway, what I recommend is go with the hybridization. Then it doesn't matter whether it is 2p, 3p or whatever. Always it is going, even though if you are having chlorine here, right? In that one you have chlorine, but for that also you are going to write sp3. You consider it as hybridized. Understand? So considering it as hybridized is better. Less chance to get wrong. Right, so that's for the first bond. Then O1 and N2. O1 and N2, here you have sp3, sp2 overlapping. And then N2C3, one of the 2 bonds is sigma, and that is also sp2sp. And C3N4, sp2. Then N4O5, O5 I think this one, no? N4O5, and that also you can consider sp2, you can say sp3, or you can say sp2 2p. And what about this one, this one? sp2, you can say sp3, or you can say sp2 3p. It's very important to write 3p, okay? Because it is chlorine. Chlorine has 3rd energy level. That's why we write 3p. If you consider the configuration of chlorine, it is neon times 3s2, 3p5. So that's why p orbitals are there to make bonds, okay? 3p orbitals. That's why you have write 3. 3. Is that clear about the sigma bonds? Not that difficult, you have to write quickly that one. And then they're asking the orbitals participated for these two 5 bonds. Okay, so both the 5 bonds are made between 2p orbitals. 2p. For this also you have to write 2p atom of carbon and 2p orbital of carbon and another 2p orbital of nitrogen. How are the two double bonds oriented in the Lewis dot dash structure given in part 3? So these two 5 bonds, what is the orientation? That's what they're asking. And they're asking you to give an example for that also, another example. If you take these two 5 bonds, the central carbon, like I said, it has undergo sp hybridization, right? And this is the carbon, okay? And it is having a p orbital which is perpendicular to this one along the bond. And it is having another p orbital which is perpendicular to this one. The perpendicular orbital. This will be along the z axis and this will be along the y axis. Okay. So when it is going to make the bonds with the two nitrogen atoms with N4, there is a sigma bond formed. This is N4. And let's say N4 is having also a p orbital to make the 5 bond. And let's say that p orbital is on the board, along the board. So then it will make this lateral overlapping and make the 5 bond along the board, okay? Like this. Okay, and you have another p orbital of carbon which is perpendicular to the board, perpendicular to the board. Okay, and that orbital will make this is the other nitrogen N3, sorry N2, and it is also keeping a 5 bond, p orbital, and that p orbital should be perpendicular to the board. That means it also should be in the same plane. It is perpendicular, right? So then those two can overlap perpendicular to this 5 bond. Understand? So what will be the orientation? One 5 bond is along the board and another 5 bond is perpendicular to the board, right? So we can write, if they ask the orientation, the two 5 bonds are perpendicular to each other. Okay, so that's what you have to write, perpendicular to each. And they're asking you an example for a molecule of iron that has a similar orientation with double bonds. Now you have to write an element that makes adjacent two double bonds. The most popular example is carbon dioxide. See, carbon dioxide is also having a similar thing. So you can write CO2 and there were some other answers also. Carbon can make two bonds with this nitrogen also. You can say, if you need. So we can say this one as CN2 2 minus, like that. We can write also. Okay, but CO2 will be the best choice to write. They're asking only one, give an example. Writing only one will be in. And they are giving you a note also, telling you that your example should not contain more than 3 atoms. And they are asking you to give the elements, use the elements from first and second periods. So that means you obviously CO2. Okay, so that's the end of part B. I hope it is okay and clear to you now. So one of my aims is doing this discussion, you have this video, right? So when you go before any test, you can refer this again and get ready. I'll tell once again about the orientation. So think about carbon. Carbon is sp hybridized. So that means there are two unhybridized p orbitals. These two unhybridized p orbitals are arranging perpendicular to each other. Is that clear? Unhybridized p orbitals. Already you know p orbitals are perpendicular to each other. No? So these two p orbitals are perpendicular. So when nitrogen want to make 5 bonds with those two p orbitals, nitrogen p orbitals also must be perpendicularly oriented. Okay, so then there will be a pi bond along the bond, and there will be a pi bond perpendicular to the bond. Is that clear? So always remember p orbitals are perpendicular. So this is your part C. An atomic orbital is described by three quantum numbers n, l, and mn. Okay, and write appropriate quantum numbers and the names of the atomic orbitals in the boxes given below. So you have to basically fill this one. So I'll just quickly say, right? If it is 3p atomic orbital, so the first number, that number 3, represents the main energy level. So in the box here, what you have to write? For this one, you have to write 3. Because it is 3p, that means it is in the third energy level. Like in the same way, for the last one, if it is 2s, you have to write number 2 here. Okay, the first number represents the main energy level. And then if it is a p orbital, then your azimuthal quantum number, the second quantum number, is going to be 1. Because if it is an s sub energy level, if s orbital, azimuthal quantum number or L value is going to be 0. Right? If it is p, then azimuthal quantum number is 1. If it is d, then azimuthal quantum number is 2. Like that, no? So then if it is 3p, it should be 3, 1. 3, 1. And we all know that p orbitals, there are 3 p orbitals, which are perpendicular oriented, as I said earlier. So those 3 p orbitals are labeled as -1, 0, +1. So here they have selected a value for us. Don't mind about that one. So normally it can be either -1, 0, or +1, any of that. But here they have given a value, so don't think about that. Just write 3 for n and 1 for L, 3p. And next one you can see, you don't have to worry about this ml, like I said. ml is -2, right? What you have to think is on these two. First quantum number telling you that it is there in the third energy level. And second quantum number, L value, gives you the sub-energy level, which is D. So you have to write 3D in the box. 3D. So 3D is having 5 orbitals. One of those 5 orbitals is given here. It is okay, right? So it may be 0 also here. No problem. Okay, so they have just given a value. Don't worry about that. And for S sub-energy level, you have to complete. It is 2S. So main energy level is second energy level. So N should be equal to 2. And L value is 0 for S sub-energy level. And ML value is also going to be 0. Because it is SA orbital, you have only one orbital. We always label that single orbital as 0. Is that clear? So go through my either previous paper classes. Okay, you have the much more explanations there. I basically explain the whole quantum number theory there. Or you can ask for the recording. Okay, so just remind this one. I know this stuff are easy for you. But if still, maybe some students are struggling, right? For those I'm telling, please go through the previous papers or ask for the recording. These stuff are not very difficult, Namaya. Everything you did so far in chemistry is very easy. Okay, the rest of the syllabus is also easy. Don't worry. Either you have to have the proper theory knowledge and proper paper practice. That's it. Then you will never forget this. Right. So let's go to the second part. Here they're asking you to arrange these things in ascending order. Ascending order. First one is from ionic bonding, which we haven't done in our theory classes yet. But anyway, I'll tell the answer because in case if you use this recording in future for studies, you should have this melting point thing also. So it is asking you to compare the melting points of lithium fluoride, lithium iodide, and potassium fluoride. Okay, so I'll just roughly say, don't mind about this one, right? So when you learn this one, anyway, we will be doing this again in the class, right? So they're asking for the melting point. Asking for the melting point. So melting point will be higher. melting point will be higher if the stability of ionic lattice is higher. Stability of ionic lattice is high. And right now we can simply explain this one. The ionic lattice stability will be higher if bond is more ionic. Bond is more ionic. It will become more ionic. It will become more ionic if electronegativity difference is higher. Electronegativity difference. In short, we say delta En. If delta En is higher, then it will be more electronegative, it will be more ionic, and then it will be stable and will have a higher melting point. This is the logic. Okay, so we need to add few things to this explanation, right? Because if I say briefly for the video, right? Melting point depends on ionic lattice stability, but ionic lattice stability depends on not only on the ionic character. Okay, it is depending on the lattice stability also, which we are going to discuss later. Understand? For now, right? For the video sake, just let's compare this one only with the electronegativity difference. Right now, let's say who's having the highest electronegativity difference? And you have these elements: lithium, fluorine, potassium, those things. Huh? Lithium, if you consider lithium and fluorine, lithium has a higher electronegativity because lithium, sodium, potassium, will find them in the group 1. Downward the group, electronegativity decreases. Then you have fluorine and iodine. Fluorine, chlorine, bromine, iodine. So iodine also having a lower electronegativity. Okay, so if you go to the lithium fluoride, then you have lithium iodide, then you have potassium iodide. These are the combinations. So highest value and the lowest value. So this is the one with the most electronegativity difference, most delta E or highest delta E. So this should be the one with highest melting point, Kf. Then if you consider lithium fluoride and lithium iodide, lithium fluoride should have a higher value and lithium iodide is the lowest electronegativity here and the highest electronegativity in the first group. So then lithium iodide is the least electronegativity difference, one with the least electronegativity difference. Okay, so in this order, melting point changes. Understand? So write a short review on that. We will be learning about ionic bonds in not this week, in the next week. Right. So the other two can be done with our molecule knowledge. Okay. They are asking the stability and bond distance. So these are the 3 molecules given for the stability, ions actually. NO2 minus, NO4 3 minus, and NF5. So what is going to be the least stable? Least stable, or in other words, unstable. NF5 is unstable. You can see obviously if you try to draw NF5, you have to draw 5 bonds. But this cannot be happen. Nitrogen must follow octet because nitrogen can't keep more than 8 electrons. Why? It can't keep 8 electrons. Because second period elements only can keep 8 electrons. Why? They don't have 3D orbitals. But if it is phosphorus, PF5 will be there. Because phosphorus can violate octet. Because in the third energy level, you have a D sub energy level also. In D sub energy level 2, you can keep electrons. So no issue. Is that clear? So NF5 is the least stable one. So they're asking in the ascending order. So least, or this one basically doesn't exist. Okay, this is not going to exist. So that's the least one. Then if you go to the other 2 structures, you look at carefully. NO4 3 minus is this one. It will be having so many charges. But if you take NO2 minus, it is not like. So here, the next one is NO4 3 minus. And our NO2 minus will be better than that. So why this is unstable? Reason is high charge distribution. High charge distribution. So because of that, this is unstable. NO bond distance. NOCl, NOCl3 and NO2F. NO2F. So NO bond length is higher if it is having more single bond character. If it is having double bond or triple bond character, what will happen? The bond length will be low. Right. So if you take NOCl, nitrogen is the central atom. You have a double bond. NOCl3. You have to keep the octet also intact. No? So therefore you can't make any 5 bonds. Only single bonds. There will be a negative charge and a positive charge. So you have a double bond here, and here you have a single bond. So single bond is longer. Okay, so what about this structure? NO2 minus NO2F. NO2F, this is the Lewis structure. Now you can see NO is having a double bond here and a single bond here. So that means this structure is having another resonance structure. So don't jump into conclusions only. This is showing resonance. So then what is the actual NO2F molecule? Actual NO2F molecule is a hybrid of this one. Resonance hybrid of this one. Or the real structure. In that hybrid, you will have NO partial 5 bonds. So it is having single and double bond in between characters. Understand? Single and double in between characters are there. So we say bond order is 1.5, remember? So that means it should have an in between bond length for the single and double bond. Okay, so when they ask the ascending order, you have to write the double bond first. That means NOCl. Then you have this partial 5 bond, single and double in between bond. NO2F. Finally, you have the single bond, NOCl. This is the bond distance ascending order. It's a good thing. Now you remember we discussed bond angle, bond length as a separate day. Right? So they haven't asked you to ask us to teach these bond angle, bond length separately. But anyway, by doing that discussion, I know you got a better practice. I know most of you can do these things now. Understood? So that's the end of our first structured essay 2019. Now I will share the marking scheme as the PDF. Okay. Look at the answers for the first 6 questions. We got these answers, and then look at the Lewis structure. Draw it separately. Okay, we will get 6 marks for that one. If you forgot to draw at least one lone pair, then no marks. Okay, have to draw it 100% okay. Then remember to put this resonance arrow. And to writing unstable also, you are given marks. And this is the table. See, you can write V shape also. That is another name. And see, you can write either 2p or sp3. Any choice. All that 2p orbitals, and here this is what you ask. You can write these alternative answers. Double bonds are perpendicular to each other. Or you can say sigma bond is linear, 5 bonds are perpendicular. So still they are given the same marks, okay, you can see. And these are the other examples. CO2, I forgot this one, NO2 plus is an example. Draw these molecules, okay. C2, CN2 2 minus I gave, and N3 minus also acceptable. Because they are limiting the options. Now you have to write this one using the elements in first and second periods. Answers for the quantum number thing. And then you have answers for the stability and other things. Okay, so 100 marks. Okay, so this is your 2021 A-level paper. So 6 sentences in the part A. You have to write those statements whether they are true or false. rules related to polarizing power of cation and polarizability of anions predict that the melting point of KBr is higher than the lithium iodide. The answer is true. Okay. So for the recording sake, I will tell potassium, and when you consider potassium and lithium, right, polarization power is lower for potassium. And if you consider the Br minus Ni minus anions, polarizability is lower for Br minus. Then you can see K plus is having a lower polarizing power and Br minus is having a lower polarizability, right? Lower polarizability. Okay, which means, okay, if polarizing power and ability are lower, then it is going to be more ionic. Understand? More ionic. Okay, so if the, like I said earlier in the 2019 structured essay, if the ionic nature is more, then it is going to be more, having more melting point, higher melting point. Understand? So then it predicts, it's true, it is predicting that KBr is having a higher melting point because K plus is having a lower polarizing power and Br minus is having a lower polarizability. Okay, so if polarizability and power are lower, then your ionic character is higher. Remember like that. Okay. So that's the answer for the first one. True. You had to write TRUE in the space. Okay, don't write T only. They are not going to give marks. You have to write the TRUE. Right. So second one onwards we can discuss. We know the theory part up to that. Right. Look at that. The electron gain energy of beryllium is positive. Okay, so what is this electron gain energy means? For the beryllium, it means you take a beryllium gaseous atom and you give an electron to that. Then it will become beryllium minus. So this value is going to be a positive value. Okay, so what it means, if Eg1 is going to be positive only for these things, okay? All group 2 elements, group 18 elements and nitrogen. Because why? Because they are having stable electronic configurations. If the electronic configurations are stable, then they are not likely to accept electrons, 2s2, 2p3 for nitrogen. And all these configurations are stable. Therefore, less does not like the, because they are having a stable configuration. So beryllium electron gain energy will be positive. Positive means, in other words, we say endothermic. You have to forcefully put the electron, you have to supply energy to make this reaction happen. Okay, so that statement is also true. That is, statement is also third one. It is asking about the emission spectrum. Spacing between two adjacent lines in the given series decrease gradually in the direction of decreasing wavelength. We'll draw that one. If this is the emission spectrum, this is your first line, it's thicker. Now you can see towards the direction of, this is the direction of decreasing gap. Here you have a gap of X and here you have a gap of Y and gap of Z, like that it is decreasing. Gap is decreasing. Okay, so we know that towards this direction, our energy increases, frequency increases. Then as a result, what should happen to the wavelength? It should decrease in that direction. So wavelength decreasing direction means, right, increasing energy direction. So what is the statement is telling? Spacing between the adjacent lines decrease gradually in the direction of decreasing wavelength. No. This is the, yeah, this is true, no? Yeah, this is the decreasing wavelength direction. So our first one was true. Second one was also true. Third one is also true. Okay, Lama? Then go for the next one, fourth one. De Broglie wavelength associated with N2 molecule is shorter than the de Broglie wavelength associated with O2 molecule when they travel at the same velocity. So de Broglie wavelength is equal to h over mv. So if the speed is same, then their de Broglie wavelengths are depending on the mass. Depending on the mass. So it is directly inversely proportional to the mass. So one with a higher mass should have a lower de Broglie wavelength. If you consider O2 and N2, O2 relative molecular mass is 32, 16 times 2. N2 relative molecular mass is 28. So this is more heavy. If it is heavier, then it should have a lower wavelength. So if it is nitrogen, then nitrogen is a lighter one. So then it should have a higher de Broglie wavelength for the nitrogen. So it is telling nitrogen is having shorter de Broglie wavelength. No. Nitrogen should have a higher de Broglie wavelength. Understand now? So this one is false. Effective nuclear charge felt by the valence electron of carbon is greater than the effective nuclear charge felt by a valence electron of nitrogen. So what will happen to our effective nuclear charge? It is increasing across the period because as the number of protons increase, nuclear charge increases. Understand? So now it is telling carbon is having a greater value. So it is wrong. Why? Because ZEFF is equal to nuclear charge minus shielding effect. So when you consider across the period, right, nuclear charge increases more than the shielding effect. Shielding effect is also increasing, but nuclear charge is increasing more than the shielding effect. So as a result, nitrogen will have a higher effective nuclear charge. Okay, because carbon, nitrogen, oxygen, that's how they are arranged in the period. And the last one, all CO bonds in H2CO3 are equal. All CO bonds in H2CO3. So to give an answer for this one, let's draw H2CO3. Right? If you draw H2CO3, you will see the Lewis structure is going to be like this. Now, when you see this one, you can obviously say this is wrong. Why? Because if you check the H2CO3, actual structure is a hybrid of this one. So don't jump into conclusions by looking at this one is a double bond or this one was a single bond. That's not the way we tell it, right? And we draw the resonance structures. That's how we decide. When you draw resonance structures, this is going to be unstable. This is also unstable. You can see our H2CO3 is a resonance hybrid of these two structures, these three structures. But the thing is, this one is a stable one, and these two are really unstable. Because of that, even though you can see that 5 bond is exchanging, you can't say the bond lengths are equal. Bond lengths are going to be different. So this is also false. Understand? So we did a very nice explanation, I remember, about the bond length of different instances using the resonance principles. I don't remember exactly the paper. Maybe it is paper 13 or something. 13 or 40, I don't remember. Right? So anyway, go through that one, that recording. Maybe you have a review also. Right? So you will have a very clear idea about the bond length. Okay, so my advice is don't just decide the answer by looking at the Lewis structure. Okay. From Lewis structure, you can't say, but right now you may have a problem where this hydrogen is connected. So in later theories in chemistry, you will learn that this hydrogen is acidic. Right? This hydrogen is acidic. Acidic hydrogen is connected to oxygen. That is the way. Acidic hydrogen is connected to oxygen. So that's why these two hydrogen atoms are added to oxygen. So you will learn it later, but you can note down that one. Anyway, you will see it later in another lesson. Like you have to consider the hybrid to say an answer. But this is why if this question is asked for carbonate, then the bond lengths are equal because carbonate is a resonance hybrid of these three structures. You have three resonance structures. You can see that 5 bond is changing the location. So real carbonate is a hybrid of all these three. Because of that, bond length is equal. But here it is, they ask it for H2CO3, no? So therefore it is wrong. Any doubt on that one? That's how the 6 questions are going to be ended. And interestingly, they are asking about the oxidation state. That's a new thing. Anyway, I think we did that part in the class also. Right, so Cl2O4. Cl2O4. So ClO, this is the skeleton. So with the practice now we know, right? If halogen stay as a peripheral atom, it is making a single bond. In oxygen, in this case, should keep 2 lone pairs for it to have no charge. Okay. And then in this case, chlorine should keep 7 electrons. 1, 2, 3, 4, 5, 6, 7. Then for each oxygen, it must make a double bond and keep 2 lone pairs for each. So if you follow our earlier method, the Lewis method, also you will end up with the same structure. Okay. I'm really encouraging you to go to the fast method. But actually the fast method is built on the Lewis method. Okay, so first of all, try to practice very well the Lewis method. Then eventually you will be able to draw these things fast. Okay, right now let's go to that oxidation number thing. So they're asking you the oxidation numbers of the Cl1 and the Cl2 atoms. Okay, oxidation numbers. Oxidation states. So how do we decide this oxidation state? So it's purely depending on the electronegativity differences. Now, if you consider this chlorine and oxygen makes a single bond. Now, that single bond electrons are attracted more towards the oxygen. So in that way, we can say the central chlorine lost 1 electron partially. So oxidation number is the number of electrons lost or gained. Lost or gained totally or partially. Now, if let's say if it is losing 1 electron, then oxidation number is +1. To indicate that it lost, we say +1, lost 1 electron. So here it lost 1 electron, so oxidation number should be +1. Then what about the oxidation number of oxygen? It is not relevant here, but oxygen has gained 2 electrons partially. If you mark the dipole moments of the other one also, you will realize that. Oxygen is gaining 2 electrons partially. So oxidation number should be -2 because it gained 2 electrons and it gained that one partially. So, it gained 2 electrons and gaining indicated by negative, and the 2 electrons is -2, -2. Okay, and they are asking the oxidation number of the central chlorine also. You can see it is losing 7 electrons. So oxidation number is +7. Then let's go to the next part. They are asking you to draw the resonance structures of this molecule. We can follow the same principle we used for the 2019 question. We can change the location of the 5 bonds. As you can see here, it is having only 1 5 bond. Only 1 5 bond. So you can put that 5 bonds for the either sides. Okay, so the two structures will be, one will have a 5 bond in the other side, and this one will have the 5 bond here. Then these will have charges. Okay. These two are the structures. Is that clear? And you can see both of them are unstable than the given structure. Usually they are giving you the most stable structure. Why this is unstable? Because you can see similar charges are adjacent to each other. That's why it is unstable. Okay, so you need the VSCPR pairs, electron pair geometry, shape, and hybridization. Right. So it is having 3 VSCPR pairs. So trigonal planar electron pair geometry, and angular shape, and sp2 hybridization if it is having 3 repulsion units. Same numbers will come for this one also, 3 repulsion units, but now all repulsion units are bonds, so therefore shape is also going to be trigonal planar. Hybridization is same sp2. And this carbon, you can see it is having only 2 repulsion units. This triple bond we consider as one lone pair. So it's going to be linear and linear electron pair geometry and shape. And hybridization is sp. Now, earlier question, you remember the sp hybridized carbon made 2 5 bonds to the either sides with adjacent 2 nitrogen atoms. But here it is making a triple bond with the adjacent single side. Now, these 2 5 bonds are also perpendicular to each other. Understand? And this one is having 2 repulsion units, N4. And there is also linear sp. I hope those things are simple for you. And then we can go for the bonding thing. And N1F, this bond is made between either 2p sp2 orbitals, or you can say sp3 sp2 orbitals. And then N2 and N1 and C2, you can say sp2 sp2. And then C2 and H, this bond, sp2 and you can say 1s. That is a special thing for the hydrogen, okay? You have to say 1s. Don't just say s, okay? And there is no hybridization for that. You have to always write 1s. Then C2, C3, you can say sp2, sp. And C3, N4, again this sigma bond, we can say sp, sp. And finally N4 and oxygen, you can say sp, sp3, or you can say sp2p. Oxygen is in the second period. Those are the sigma bonds. And 5 bonds, there are this the 5 bond and there are the 5 bonds. All 5 bonds will be 2p, 2p. 2p, 2p. All 5 bonds will be 2p, 2p. So this 5 bond is 2p, 2p, lateral overlapping. Okay, you have 2 5 bonds, they all will be 2p, 2p. Understand that? 2p, 2p. Right, and they're asking you the bond angles around N1, C2, C3, and N4, the central atoms. So bond angle around this one, trigonal planar with one lone pair. So it's going to be 117.5 because we have to subtract 2.5 for one lone pair. I'm going to draw that later and explain. Huh? And then C2, we can say 120 approximately. Maybe a little bit different because of the double bond. And these two are going to be 180 and 180 because they are linear geometry, no lone pairs. So if you have a lone pair only, then subtract 2.5 from the ideal bond angle. This is called as ideal bond angle. Okay. So so if you try to draw this one, like I promised, right? Try in this way. This is hydrogen and this is the carbon and nitrogen and oxygen. So N1 nitrogen, this is C2 carbon, C3 and N4. And then you have a fluorine, there is a lone pair, and that fluorine is right here. This is how you are going to draw it. So like I said, if there is a lone pair, then it push more. So bond angle is going to be lesser than 120. So that's why 117.5 is written. And this one approximately we can say 120. Approximately 120. Because bond angle, if you get the exact bond angle, it's going to be different. So one can write this bond angle is more than 120, 121. And this one is going to be lesser than 120. So 118. Like that you can say. But what you have to write for the exam is 120. These are, you can say linear. So 180, 180. Understood, Lama? I hope it is clear. So try these things, try to draw. And if you are not sure, you can ask me by sending a photo or something. I can tell whether it is correct, or if there is a mistake, I can correct that. Okay, and the last part here, they're asking the electronegativity increasing order for the N1, C2, C3, and N4. We did this one actually last week in the class. So electronegativity, first of all, you have to compare according to the Pauling scale. Nitrogen is more electronegative than carbon. Then compare the two carbon atoms. First carbon C2 is sp2 hybridized, and C3 is sp hybridized now. So then that means this is more electronegative. Okay, so then C2, C3. Then take the two nitrogen atoms. This one is sp, which should be more electronegative, and the other nitrogen is sp2. It's going to be N1 and N4. This is the electronegativity ascending order. Before applying scope, remember scope from our last week discussion in paper class also reading. Before applying scope, make sure you understand what is more electronegative according to Pauling scale. Apply Pauling scale first. Understand? After that, to compare between same element atoms, use scope. That's what you need to do. Okay. Right. An interesting part is there for the part C. I'll show you that quickly. Okay, so it's asking the wavelength is 695 nanometers. First thing they're asking which region it is belonged. So which region it is actually belonged. We know our visible range is there from 400 nanometers to 700 nanometers. So this value is less than 700. Right? So it is there in the visible region. So laser is actually a visible thing, no? Understood? So the region in the electromagnetic spectrum is visible. And they're asking energy of 1 mole of photon. Have given the speed of light and the Planck's constant. So how do we find the energy of 1 mole? Energy of 1 photon can be found using Planck's equation. Hc over lambda. Lambda is the wavelength. If you need the energy of 1 mole, then what you should do? Multiply energy of 1 photon by Avogadro constant. Right? And apply the values. 6.63. Use the value they have given. Okay. 10 to the power minus 34 joule seconds. You must write units. When I show you the marking scheme, check there. 3 into 10 to the power 8 meters per second. And Avogadro constant is 6.022 into 10 to the power 23 per mole. And lambda is 695. I will write it as 695 nanometers. Right? That means 695 into 10 to the power minus 9 meters. It is nano. Then we can further simplify this one. 6.95 into 10 to the power minus 7. Okay, 6.95 into 10 to the power minus 7 meters. Now, you can see these things are not going to be divided. Okay, so if you don't have enough time to simplify, just leave it here. Okay, without adding the answer. Later, if you have time, you can simplify it. Okay, so anyway, these are the numbers you need to simplify. 6.63 into 3 and 6.022. If it is MCQ, we know how to round it off and get, no? Simplify this one separately and the 10 to the powers. 10 to the power minus 34 and 8, 23. This one give you 31 and minus 3. And my 10 to the power 4 joules per mole. This is the unit. So if you want to convert it into kilojoule per mole, what you should do? Divide this one by 1000. Divide this one by 1000. So your final answer is going to be 66.3. I note it as 66.3 by adding that 10. Okay? Into 3 into 6.022 when you're multiplying 6 using 6 is enough. So it's almost 6 now. And then 6.95 you can use 7 during the multiplication, simplification. Okay. Then you will get a proper answer, don't worry. A little bit low, a little bit, maybe the very closer to the real answer. Okay. Kilojoule per mole. Understood that one, Lama? No? Right, now I'll show you the marking scheme before go to the next part, because we can find the correct answer for this simplification also. You can see where they have offer marks. For writing energy of 1 photon, they gave 1 mark, that equation. And for the mole of photon, 1 mark. And for the proper substitution, 3 plus 1. That plus 1 is given for units. Okay, and finally, 172 kilojoules per mole will come. Okay, you will only lose 2 marks. Okay, from the 100 marks they gave, you can score 98. That is enough. Okay, Bute. I'm telling you about the time. Okay, if you don't have enough time, just leave it. Because if you're trying to get that 2 marks, it is going to be actually 2 of the 1,000 marks, right? It's not that worth. Okay, because it is taking time. You will realize these things when we do more papers like that, where if necessary we have to leave things. And these are the answers for the rest of the things. Look at this: true, 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 false, false, false. We got that one correctly. And yeah, here they are accepting ticks or T's, but anyway, write true. And then see the Lewis structure, oxidation numbers. Use the +1 and +1 and +7 numbers. Okay, don't use these Roman numbers, even though they have given it. And these are the resonance structures and the table. You see the orbital identification. So like your friend asked earlier, it is not always going to be 2p. Okay, if it is nitrogen, sulfur was there, it will be 3p. And then these are the oxidation bond angles. And you can see plus or minus 1 is given. So you don't write plus or minus 1. Okay, they are asking an value, no? So you have to give a specific some value. Right. And let's go to the last part. So last part is from our previous discussion about polar, non-polar molecules and polar, non-polar molecules. Yes, let's quickly do that too. A molecule of a formula AX3 has 3 AX sigma bonds. Okay, here A and X represents the symbols of elements and A is the central atom. Name the molecular shapes possible for the AX3 and for it to become polar and for it to become non-polar. AX3. So AX3, if it is what they are first asking, polar. No? If it is to be polar, you can just remind some examples. NH3, which is polar, like that. So then possible, we are asking for the shape, right? Shape, yeah. Shape is, you can say, trigonal pyramidal. Trigonal pyramidal is one shape. And they are not only asking for one, okay? Possible shape or shapes. So if there are more, you have to write. So this one may not come to you directly, even though you write NH3. The second, there is another one. This might not be coming to you so quickly, but with more practice, you will actually. Remember a molecule called ICL. ICL, how did we draw that? It was having trigonal bipyramidal electron pair geometry and T-shape. Remember. And T-shape is also correct, because this is also going to be polar. These are the two answers you have to write. Okay. These are the examples. They are asking you the examples later. If it is to be non-polar, what it is going to be? Trigonal plane. It's very simple. Trigonal plane, you can give answers BF3. Okay. In the second one, they are asking, give one example for each. So you can write these examples. Is that clear, Lama? It is becoming non-polar when the resultant dipole moment is 0. Okay, resultant dipole moment is 0. Get the answers. T-shape, trigonal pyramidal or pyramidal. You can see they have offer marks separately, so you have to write both. And then if it is non-polar, answer is trigonal planar. And the examples. You have more examples than I gave. So get use of that. If shape is wrong, do not award marks for the examples. That's fair. Okay. Yeah. Shape need to be indicated to awards the marks for the third one. So you have to say T shape and write in front of that an example. Without that, nobody knows to which shape you wrote that example. So see when you look at the marking schemes today, you will understand what to write and how to write. Understand? That's the way. Okay. Now I hope you had a good idea, good kind of reminding about the first and second unit questions that are coming for the A-level exam. Okay, so this structured essay, you have to, if possible, try to get 100 out of 100. When we give exams, usually there are students who score all the marks of this structured essay, right? And for the upcoming test in this month, I'm going to keep, okay, you will have a similar question, right? So I'm going to finish the class for today. Study well. See you all again in the next class. Keep writing reviews and complete these things in your tube itself. In our next week also, we're going to discuss another 2 structured essay questions. Okay, right. So goodbye everyone. Study well.